Alright, so we're going to start our chapter on linear momentum. And I want to kind of tie it in immediately with the idea of conservation of mass. So we found out that the law of conservation of energy is one of the conservation laws that's super duper helpful when we're looking at physical concepts and trying to solve physical problems. There's other conserved quantities besides mass and besides energy, and some of those conserved quantities include momentum, and I'm going to specify linear momentum, or momentum when an object is traveling with translational motion. That's what we're going to be studying in this chapter. There's electrical charge, which is conserved. For every positive charge there exists in the universe a balancing negative charge. And angular momentum, which we consider separately from linear momentum, and that too is a conserved quantity. And because all of these are conserved quantities and we can apply laws of conservation to them, they're going to be really important fundamental property concepts that we can use to study and solve most or all of our problems. So we start with this basic idea that linear momentum is conserved, and that because linear momentum is conserved, we can say that there's a tie-in with Newton's second laws, and actually the conservation of momentum is just a rework of Newton's second and third law, and we can show that momentum is conserved by showing that Newton's second and third laws go together in these fashions. So that means that if you take Newton's laws and rework them, you could be a master problem solver with the full science power at your liberty. So that means that even if you started out rusty on the equation solving for momentum, if you are solid in your Newton's laws, you can reach your conservation of momentum problems just with forces. So let's look at what we can use conservation of what we can use conservation for. The first thing that we look at is we can use conservation of energy and conservation of momentum to analyze collisions. And in fact, most of the situations that we're going to be looking at throughout this chapter are going to be collision or collision-like situations. And I'm not just talking about car crashes. Pretty much where any two objects come into contact with each other, there is a collision to be had, or a collision to consider. And so that means that when two objects are interacting with each other, we can most often use conservation of energy and conservation of momentum ideas to solve those problems. Conservation of momentum is especially useful for analyzing systems of two or more objects that interact, like in collisions. So you're most likely going to want to use conservation of energy and conservation of momentum ideas before you use other concepts in physics. So before you use forces, before you use kinematics, if you have a system that has two or more objects, it will always be simpler if you can use the conservation laws as opposed to breaking them down and analyzing them separately. So that means that these ideas, and when I say these ideas, I mean the conservation laws, as they apply to two or more objects, will also lead us to look at the center of mass and deepen our understanding of what the spherical cow is, and then we're going to break free of that model leading into the next unit. So what is the spherical cow model? The spherical cow model is saying that an object, super complex, like a cow, which does all of its cow-like motions, like picking up and bending its legs, and like swishing its tail back and forth, and twitching its ears, and moving its head from side to side, and being milked. If you took the sum of all of those motions, then what you would get is you would get one cow that acted like a tiny spherical perfect particle. There it is, there's our spherical cow. And we could analyze the sum total of all of its motion and be able to treat that cow as if it were one tiny little particle moving through space. And that's what we study when we study linear and translational motion of any sort. And that's what we're going to continue to do. By understanding what the center of mass is, the center of mass is actually this tiny little point in space that we call the spherical cow. We are going to be able to continue to apply all of these major concepts like conservation of energy and conservation of momentum and how objects interact with forces. And then when we need to look at the bigger picture, for example, say our spherical cow is actually rolling down a hill, then we can take a step back from the center of mass and look at the cow as a whole piece instead of just a translational point-like object. And that's going to be our convergence point from momentum into angular motion. So remember I said that momentum is actually just a rework or a restatement of Newton's laws. And that's actually very true, and so that's where we're going to start, is connecting momentum to Newton's laws. A few things I want you to know is when I say linear momentum, or when we're talking about linear momentum, it's most often just stated as momentum. So I don't have to say linear momentum every single time to specify that I'm talking about linear momentum. In fact, when we say momentum, we are almost always talking about linear momentum. It's given by the symbol rho, which is our funky p. And what momentum is it's the product of an object's mass multiplied by the object's velocity. So expressed in an equation, it would be rho equals m times v. And you notice that I've got my little vector symbols above both the velocity and the momentum, and that's because since velocity is a vector, momentum is a vector. So we're back to vectors. We took a brief break from vectors and saying that work and energy were directionless. They had positive quantities and negative quantities, which meant that they were added or removed from systems, but they were directionless. We're back to things having direction. Momentum is based on velocity. Velocity is a vector, therefore momentum is a vector. So something to think about or associate with, right? Force and acceleration are vectors, and when we're talking about net force in particular, the net force vector and the acceleration vector always have the same direction. When we're talking about circular motion, since there's centripetal acceleration, that means that there is centripetal force, and they're in the same direction. It's impossible for them to be in different directions. When we're talking about free body diagrams, right, the net force and the acceleration both have the same direction. So that means that these vectors that are dependent upon one another, like the relationship between force and acceleration, and the relationship between momentum and velocity, they must, in fact, have the same direction. So that means that for an object that is moving in a circle, its tangential velocity, right, it's tangent to the circle, 90 degrees to the acceleration. Therefore, the momentum likewise is in that same direction because those vector quantities are going to be equivalent. And remember that velocity depends on the frame of reference. If you're riding in a car at 20 miles an hour with your best friend, you and your best friend both feel like you're at rest. You're sitting there. But according to the frame of reference of your other friend that you left behind, you're driving away from them at 20 miles an hour. Therefore, since velocity is dependent on your frame of reference, so is momentum. And so that means that it's going to be important for us to remember that we want to be problem solving in an inertial frame of reference. If your frame of reference is accelerating, your values are not going to be very functional. And then we talk about the units of momentum. Right? The units of momentum are the units of mass times velocity. Therefore, momentum is kilograms times meters per second. And we don't have any special symbology for it. Remember, when we talk about a Newton, it's a kilogram meter per second squared. And a joule is kilogram meters per second squared times meters. But momentum is given by mv, and the only units we can use are kilogram meters per second. All right, those are the units, no abbreviation. So let's think about all these situations where momentum as a value matches up with what you think of as momentum in your day-to-day life. First, let's consider two cars that have the same velocity. So that's what's given here. They're the exact same velocity. So we could say it's 20 meters per second, for example. All right, if those two cars have different masses, this is a small car with a small mass, this is a big car with a big mass, that means that if the velocities are the same, the car with the bigger mass will have more momentum because mv is going to be less than mv just by virtue of the fact that the mass is bigger. So that kind of fits with your idea of what does and doesn't have a lot of momentum. Likewise, we could say that a giant truck moving very fast would be expected to have a very big momentum compared to a tiny little motorbike with a tiny little velocity. All right, this would have a huge momentum, this would have a little momentum. So when we think about what momentum really is just how hard an object is to stop in its motion. And so a big old truck moving very fast is going to be very hard to stop. You would not want to stand in front of that truck. Whereas if you're looking at just an oncoming motorbike, you might not like it, but you're going to be relatively ambivalent. You might be able to survive this because there's going to be less force involved in the stopping situation here, but there's a huge force involved in the stopping situation here. You're likely not going to survive that if you're unprotected. So we could say the more momentum an object has, the harder it is to stop. And that brings us to the football situation. If you had a choice between being tackled by Big Benny or Little Benny, and you were going to compare them, we'll say that Big Benny has mass m, and Little Benny has mass little m. If Big Benny will more than likely be able to go very fast, and so Big Benny will have a very big momentum. However, Little Benny will have a very little momentum. Therefore, you are much more likely to be willing to be tackled by Little Benny than you are by Big Benny, just because since it's going to be harder to stop Big Benny, that means that there's going to be more force involved in that stopping process. This is why there's so much more shock involved and so much more impact involved in getting tackled in pro football compared to, say, Pee Wee football. It's why the injuries are bigger and the damage tends to be a little bit more permanent in those situations. So if it wasn't intuitive up to this point in time, we can think that a force is required to change the momentum of any object, right? Because in order to change an object's momentum, we have to change its velocity. The only way to change a velocity is through acceleration. If there is acceleration, there is a force. So that means that it's going to take a force. They can increase momentum by using a force that would be accelerating in the same direction of the velocity, or you could decrease momentum by applying a force in the opposite direction of velocity, or you could change the direction of momentum. That would be in a situation, say for example, an object moving in a circle. And it turns out that the Newton's laws were actually written in terms of momentum before. We've always thought of them in terms of force and acceleration. Force equals ma, and the relationship between force and acceleration. But Newton actually stated his laws in terms of momentum, and we derived the more familiar form of F equals ma from his statement. He said in his second law, he said, the rate of change of momentum of an object is equal to the net force applied to it. So his statement was actually that the net force is going to be proportional or equal to the change in momentum over time. That's the rate of change of momentum. And that will give you the magnitude of force that was caused. So what I want to do is I want to take a look and see if it really is the same thing as the net force equals mass times acceleration, which is what we're familiar with, and we've been able to observe and record data showing that it's true. So we're going to skip the part where we have to show with data that it's true for momentum. We're going to start with this statement that says what Newton originally said, that the net force is going to be equal to the change in momentum over the change in time. If momentum equals mass times velocity, then we have final momentum minus initial momentum over time. Since the mass did not change in this circumstance, what we do is we factor it out, and we get the equation mass times v2 minus v1 over time. And you notice that v2 minus v1 is our classic statement for change in velocity, so we rewrite that as mass times change in velocity over change in time. If, because of my order of operation, I pull the mass out of the fraction, then I get mass times change in velocity over time. And you can recognize change in velocity over time as your classic value for acceleration. So in fact, this equation right here truly is exactly the same as the equation that we're more familiar with that says force equals mass times acceleration. It is force equals mass times acceleration. So this equation can also be used to solve any dynamics problem. So the net force is equal to the rate of change in momentum, and this is a really great equation because it's actually more general than our equation that we've been using for force equals mass times acceleration, because the change in momentum could be caused by a change in mass. Situations where mass might change might include times like when rockets burn fuel. This is also going to count when your car burns fuel. Only in those circumstances the changing mass is much less, but it still actually has an impact. So we could think like when a rocket moves, that rocket has to do so by burning fuel. That fuel was contained inside of it as a liquid. When it's ignited with oxygen gas, or when it's ignited with hydrogen, as is done in space so that it can burn without oxygen, what happens is the liquid in there is converted into gas particles like carbon dioxide and water predominantly. And those gas particles get left behind as leftover mass. Meaning that the overall mass of the rocket after it's burned is going to be less than the mass of the rocket before it was burned. So that's going to mean that the change in momentum will have happened as a result of the change in velocity of the rocket as it moves or as it accelerates, and the change in its mass as it loses fuel mass. The change in momentum over time equaling force is also useful when we're talking about the concept of theory of relativity. So it starts to matter more when we talk about objects that are moving very, very fast, often at the atomic level, where the faster an object goes, the more massive it generally becomes. So let's go ahead and let's take a look at a calculation that we could do with this concept of force equals change in momentum over time. We're going to take a look at the force of a tennis serve. A top player, like pro tennis player Benny, can, upon a serve, make the ball leave the racket with a speed of 55 meters per second, which is about 120 miles an hour. If we assume that that ball has a mass of 0.060 kilograms, and that it was in contact with the racket for about 4 milliseconds, we could actually estimate the average force that the racket applied to the ball due to bending. So here's how we're going to do that. The first thing that we want to do is we want to consider, because our equation is net force equals change in momentum over change in time. So we would have a free body diagram for our ball where the force of the racket is a forward force and it's immense. The ball is in the air, so it also has this mg force down. But consider, if you will, the size of the force of the racket striking the ball versus the size of the force of gravity pulling down. Once the force of the racket striking the ball has been removed, gravity will be the only force acting on the ball, and the ball will be in free fall. However, during the time of contact, that force of that racket is actually huge. So we're going to temporarily ignore the force due to gravity when we're calculating our net force, and we're going to assume that the net force is predominantly made of the force of the racket striking the ball. And that's actually an important thing for us to do, or consider that we could do very reasonably. Just like we did when we were talking about circular motion, right? And we said that technically there's some angle here, so that means that there's going to be an ftx and an fty for a swinging object. But we said that the fty, to balance mg, was so small compared to the overall force of tension that if we approximated the force of tension to be only along the x-axis, we would get a very reasonable answer. So we're using that same concept here. And we're going to apply Newton's second law written for momentum. So we're going to say that the net force here is equal to mv2 minus mv1. Now let's consider the situation that we're looking at. We're looking at a ball striking a racket. So we're going to assume that the ball, during the serve, before it was struck by the racket, in the instant before, we're going to assume its velocity was 0. So that means its initial momentum was likewise 0. And we know that the time interval was 4 milliseconds, or 4 times 10 to the negative third seconds. So when we plug this in, we're going to plug in that the net force that caused that ball to accelerate was 0.060 kilograms times 55 meters per second divided by 0.004 seconds. And if we calculate that out, it actually ends up being approximately 849 newtons, which, to one significant figure, which is, we're limited by time, which is one significant figure, would round down to be about 800 newtons. That's a huge force. In fact, the question asks, is this force large enough to lift a 60 kilogram person? And so we'd have to know, if we're lifting, then the minimum force required to lift a person is going to have to be equal to mg. So a 60 kilogram person would require a force of approximately 600 newtons to lift. And 800 newtons is definitely bigger than 600 newtons. So this force that causes the tennis ball to accelerate to 55 meters per second is not only big enough to speed a tennis ball like that, but it's actually big enough to accelerate a person upward. It's going to be mg plus more. So that person is going to have a net force in the upward direction, or accelerate upward. That's how large this force is. So that's pretty impressive. So let's take a look at a few assumptions that we made, or a few concessions that we made in order to do this problem simply, or to come up with some pretty accurate answers without having to do exact answers. The first thing what we said is the force of gravity on the ball, which is the mass of the ball times acceleration due to gravity, is actually only 0.59 newtons. If you compare 0.59 newtons to 800 newtons, you're going to notice that that's paltry by comparison. It's 0.59 is about 0.5% of 100 newtons, and 100 newtons is about a 1/8 of a percent, 1/8 of 800 newtons. So we're actually at 1/16 of the overall force that's required. That's such a small amount, 1/16 of a percent. So that'd be 0.0000116, like 4 of the total force. So obviously, when you compare the force of gravity, which is so small, to the actual impact force, we can disregard how much of an impact that has and still have a pretty accurate answer. In fact, our percent error on that would be less than 1% by quite a bit. So we get really accurate answers when the force that's causing that action is much larger than any external force like the force of gravity. Another thing to note is that radar and high-speed photography can give pretty good contact time estimates, like how long the ball is in contact with the tennis racket, how long a person's feet are in contact with the ground when they're pushing off, how long a fist is in contact with the face during a punch. But measuring the force in those situations isn't really practical because that force usually is variable. So that means that calculating change in momentum, which is easy to do if you know the mass and change in velocity, is a great way to do estimations of forces in these sorts of circumstances. Let's take a look at another example where we're going to be looking at washing a car. And this is going to allow us to look at the change in momentum and the forces that are involved. So the question asks, if water leaves a hose at 1.5 kilograms per second, and this is, sorry, that's better. What is the force exerted by the water on the car? So let's think about what situation we're actually considering. We're considering this situation right here where the water is striking the car. So that means that we're going to be looking at the net force of that, water striking the car, is going to be equal to the change in momentum that occurs right there over the duration of time that it occurs over. So what's changing momentum here? The only thing that I can observe changing momentum is the water itself. The problem says that we're going to ignore any splashback, which means that when the water hits the car here, it stops. So that means that our change in velocity is going to be from 20 meters per second to 0 meters per second. And so that means that if we had our change in velocity, we'd have v2 of 0 meters per second and v1 of 20 meters per second. So we have a change in velocity of negative 20 meters per second. And now we're looking for our mass and our change in time. And we don't have a direct mass or a direct time. All we have is a rate at which the water leaves the hose, which gives us how many kilograms happen every second. And that's a ratio of mass to time. And that ratio of mass to time, which is found right here, can be used to find the change in momentum, or the rate of change in momentum, which means we can use that 1.5 kilograms per second, times it by the negative 20 meters per second, and we'd get an overall net force here that's equal to a negative 30 newtons. Now let's think for a second. This force is negative 30 Newton force. It's the force that caused this water to stop moving. So that means that that force was in that direction. That force is actually the force of the car on the water. But the question asked for us to find the force of the water on the car. So now we must consider Newton's third law, which says that all forces come in pairs. So if the car applies this 30 Newton force on the water to the left, then that means that the water applied that exact same force to the car to the right. So that means that the net force of the water on the car is equal to a 30 Newton force. And that happens every single second because that's the rate of change of momentum. So that gives us something else to consider. We want to make sure when we're solving problems like this that we're keeping track of the signs, right? I had a negative 30, and that negative 30 was actually a result of the fact that I was calculating the change in velocity and the change in momentum for the water. So that negative 30 was the force that caused that water to change. And then I had to think about what the relationship of that force is to the force that I actually wanted to solve for. And I got a positive 30 there. If I keep track of my signs, I will always make sure that I have the right answer, but we could also use common sense. Take, for instance, the idea that the water is moving to the right. So that means that if something's moving to the right and it comes into contact with something else, it's going to cause a force in that same direction. So that means that if we assume that our answer is going to be right using this idea of common sense, then we could assume that our final answer should, of course, be positive.